Hi everybody, and welcome to lecture 28 on areas and Riemann sums. In this lecture, we're going to be concerned with the idea of finding the area under any arbitrary curve. And we're going to specify for this lecture that the curve is strictly going to be greater than or equal to 0. So in geometry, you learn how to find the area of many basic shapes like squares and circles and rectangles. But what happens if you have something shaped, I don't know, like this? So just on your paper, you can just draw a curve like I am. The point is this curve is above the x-axis for the entire interval that I'm considering. And let's just say this is A, and then this is B. So if you draw some lines like this, what I want to know is what would the area of something like that be? So it's not really like a rectangle or anything, and you don't have some kind of standard formula you would use from geometry to calculate the area of a weird shape like that. So that's what we're going to be looking at today, is trying to figure out areas like that. So here's our question. So how might we calculate the area under this curve? And the strategy we're going to use today is going to involve approximations, and then we're going to show how to take our approximations and actually approach the true area. So let's start by learning how to approximate areas using familiar shapes. So I'm going to be using rectangles in this video. So here's our example. So let's say using a left endpoint approximation, estimate the area under the curve f of x equals x squared plus 2 on the interval 0 to 3 using 3 rectangles. And in parentheses, I'm going to write subintervals because that terminology is also used. So we're going to have this curve right here. We're interested in the area under the curve from a specific point A to B. So this time it's 0 to 3, and this is what it was in the picture before. All right, so how might we do something like that? Well, first, I'm going to go ahead and get us a picture on the board so we can see what's going on. So what I'm going to do is I'm going to draw the equation that was given. So the equation is x squared plus 2. So I'm going to start on the y-axis at 2, and I'm going to 3, 4, 5, 6, 7, 8, 9. I'm going to give myself quite a few markings here. And then if I were to plug in 1, for example, into this, I would get 3. And if you plug in 2 into the equation, you would get 6. So 4, 5, 6. So I'm just trying to draw what this looks like. And then at the end of the interval, if you plug in 3, you'd actually get 11. So I want you to make this a little larger, but it looks like something like this. Okay, and the curve keeps going on, but what we're interested in is from 0 to 3, you have the area under this curve. So we want to know the area of all that stuff under there, and it's a very odd shape. It's shaped like this. We want to know the area of that. So we're going to approximate using rectangles. So what you're going to do is you're first going to find the width of the rectangle. And the way they do that, or way you do that given the information, is we're going to call it delta x. And this is equal to the difference in the endpoints, so b minus a, over n. And n is going to be the number of subintervals that the question wants. So in this question, there's going to be 3 3 rectangles or 3 subintervals. So n would be 3 in this case. So if we're doing this for our example, delta x is b minus a is 3, and we want 3 subintervals. So the width of each rectangle is going to be 1, and we're going to have 3 rectangles. So that's what delta x is. What I like to do is I like to draw a picture at this point. So I have 0, 3, and 1 and 2. So you start with your endpoints, and you take delta x, and you count all the way up. So the distance between each of these is just delta x. And you would start at the lowest one, and you would keep taking delta x and adding it until you get to b here. So this gives you 3 different subintervals. So you can check and make sure that you have it right. So there's 3 subintervals. There's 3 sections of this number line right here. And the last thing you need to look at is what type of approximation do they want. In this class, we're going to be doing left, midpoint, and right. So you need to pay attention to which one they give you. So if they give you left, you want to look at all of the ones on the left here. So if you start with this first interval, what number is on the left? It's 0. And then if you look at this interval, it's 1. And if you look at this interval, the one on the left is 2. So these are the numbers we're going to be using in our approximation. So you need to grab the correct ones, and that's just based on which one they tell you. And then from here, what I'm going to do is I'm going to define L3. And this is going to be, it's the area beneath f of x using, I'm going to say not beneath f of x. It's going to be the area beneath the rectangles using left endpoints. So that's what L3 is going to represent. So these are my 3 left endpoints. Let me draw it on my picture now. So I'm going to start at 0 for one of my endpoints here. I'm going to make this rectangle. The next one's at 1. So we start on the left at 1, and we go over here to 2. So that's a rectangle. And then my final one starts at 2 on the graph at 2. We're here. We go over to 3, and that's the height. So these left endpoints here determine where the height comes from. And then let me shade it in. So these are taking all my rectangles from the left endpoint here. And you start on the graph, and then you go over to the right and drop it. So that's what the rectangles look like. Let's get the total area of those. So this is going to be the base times the height for each of them. So all of them have 1 for the base. So the first rectangle would be 1 times. And then I would need to know what f of 0 is, because that's the height of this first rectangle. So f of 0 plus 1 times f of 1 plus 1 times f of 2. So the heights of the rectangles are given by the function value at these left endpoints. So if I do 1 times f of 0 is 2. F of 1, if I plug that back into the original, it's 3. And finally, if I plug in 2 into the original, it's 6. So the heights of these rectangles are 2, 3, and 6. And if you add them all together, here you're going to get the area, which is going to be 11 units squared. So that's saying that the approximate area under the curve is 11 units squared. However, this is an underestimate. Underestimate of the true area. And you'll notice that in our picture, we have gaps, right? There's one right here. There's one right here. And there's one right here. So it's not quite the full area. Actually, at each stage, we underestimate it by these spots that I've circled here. So this is considered an underestimate in this case. You just look at your picture to figure that out. OK, so it turns out that the more rectangles we use, the better the approximation for the area becomes. This is because these gaps start shrinking, these rather large gaps I have here. As you use more rectangles, it's going to start shrinking what's going on. So let me draw just a little illustration of what's going on for that. I won't be so exact, but I'd like to have the same kind of picture. So this graph is supposed to mimic what's going on over here. So instead of just having 3 rectangles, let me just draw a lot. So I'm going to always start on the graph, draw out to the right, and drop it. So I'm going to go like this. And I'm just going to draw many of them like this. I kind of wanted more, but I mean, that's as many as I can draw. I'm going to connect them all like this. And you can see, you might not even be able to see in the video, but all the spots I have left here, these gaps that were left under here, they're extremely small. And as I increase the number of rectangles, it's only going to keep decreasing the size of those gaps. So as you make the rectangle smaller and smaller, here I have like 9 of them. Not the rectangle smaller, but the number of rectangles you keep increasing them, the gaps get smaller here. So the idea that you want to take away from this is as n goes to infinity, so as the number of rectangles increases to infinity, we approach the area under the curve f of x. And then it would be from a to b, of course. So that's the idea. So the more rectangles you use, the better the approximation is. All right, let's look at this example. So this says approximate the area under f of x equals x cubed from 0 to 4 using 4 rectangles with right endpoints. So right endpoints and with midpoints. So in this example, all I'm trying to get you comfortable with is using the other 2 methods we're going to use. So this was called left endpoint, where I grabbed all the things on the left side of the interval. I'm just going to show you how this one works. So first I'll have my graph. This is easy enough for me to draw. If I have the x cubed graph, it'll look something like this. And then I want to go from 0 to 4. So here I'll mark 0. Here I'll mark 4 maybe. And then I want right endpoints and midpoints. So the first thing I need to do is label this a and b and calculate the width of each of my rectangles. So delta x is b minus a over n. And following the example over there, that's 4 minus 0 over 4. That's my n. 4 rectangles. So 4 minus 0 over 4. Luckily, we get a very nice width for this. Again, it's just 1. Sometimes it's not as nice as that. Then I always launch into drawing my picture. So the 2 endpoints this time are 0 and 4. And I would mark this 1, 2, and 3. Because you're counting up by delta x. Each of these spaces need to be the same. So you count up by 1s. And notice I've created 4 different spaces this time. Before I had 3 spaces. But now I've created 4 spaces. OK, and we need to grab both the right and the midpoints of these. So let me circle all of the right ones, because I feel like that one is the easiest to see first. So in this interval, 1 is on the right. And then in this interval, 2 is on the right, and etc. So notice the only difference from the left one and the right one is all of them moved over here, and you're missing the left one. And on the left approximation, you're just missing the far right one. So that's the difference. So I'm going to say that R of 4 is going to be the area under all of these rectangles using the right approximation, just like L of 3 was using the left endpoint approximation. So let's figure out what this is going to be. So the width of each of these is going to be 1. f of 1 gives me the height of my first rectangle. So if I go to 1, that's where my first one's going to be. Here's the graph, and I draw to the left this time, and that's my first rectangle. And here's my second one. If I go to 2 on the graph, and then I go over to the left, so I start from the right, go to the left, that's my second rectangle using the right endpoint. So notice, all of these rectangles are going over the graph. So actually, I'm getting an overestimate here. And that's R4. That's the right endpoint approximation. So in this case, the rectangles I'm drawing are going over the graph, in contrast to these that were staying under the graph. So we know this is going to be an overestimate. The height of the first one is F1. The height of the second one is F2. The height of the third one is F3. And the height of the fourth one is F4. So again, all of these are width 1. So a rectangle is base times height. And because it's 1, that makes the calculation a little easier. And then we just have to figure out these points that I'm drawing on the graph. Where are those? So these points I'm denoting with these dots here. So that's the height of each rectangle. All right, and we just have to calculate that. So f of 1, if you plug that into the equation, that's 1 cubed is 1. If you cube 2, it's 8. If you cube 3, it's 24. And if you cube 4, it's going to be 64. So then the difficult part of this problem is you have to actually add those up. And I've done that ahead of time for us. That's going to be 100 units squared. And remember, we know that's a slight overestimate. This is just an approximation of what's under the curve based on these rectangles. If I were to make 8 rectangles instead of 4, I'd get an even closer a guess. It would still be an overestimate, but it'd be closer to what it actually is. So this is just a little bit over. Let's look at the midpoint. So M of 4 is going to be the area under the curve using midpoints. So what I'm going to do is first look at my picture again, and I'll do this in blue. And I'll grab all the midpoints in the interval. So in the first interval, what's in the middle? It's 0.5. So to start this, I'm going to have 1 times f of 0.5. I'm going to use that for my height. And then if you grab the rest of these midpoints, you have 1.5. And then you have 1 times 2.5. And you have plus 1 times 3.5. So I still have 4 different numbers. I'm just grabbing all the ones in the middle, or the midpoint of each of these. OK? So if I were to draw on this picture what's going on, maybe I need a new picture. So let me go ahead and do that for myself. So here's a picture. Here is going to be x cubed. Let me draw that a little better, just so I'm able to show you using a picture what's going on. It's a little crammed right now. So let me draw a graph like this. What do I want to do? I want to make this kind of taller, just so you can see what's going on. OK. So this is going to be the graph, again, of x cubed. This will be 1, 2, 3, 4. I keep adjusting this picture, but I really want to make it so that you can see what's going on. So let's go like that. OK, that's pretty good. So for this, what I would do is I'd go to the midpoint of each of these. So first is 0.5. We use this height, and we go half on either side, and that's how I draw my rectangle. Next, I go to 1.5 in the middle of 1 and 2. That's where the graph is at 1.5. You go out and out on either side and drop it. From 2 to 3, you go right in the middle at 2.5. Find that spot on the graph, out, out at that height. And then the last one will be 3.5. So starting at 3.5, you're going to go up to the graph, and then keep the same height on either side and drop it. So that's how you do it using midpoints. Notice you have pieces that are slightly under the graph and some that creep over the graph. So the midpoint is kind of like a compromise between the left and the right endpoint estimates. So draw this on your paper so you can also get comfortable with these pictures as well. But in most cases, the midpoint approximation is a nice, happy middle ground between the left endpoint and the right endpoint. All right, so if we go ahead and we calculate this using 1 for all the bases, and then the heights here, I would have, this is going to be f of 1/2 plus f of 3/2 plus f of 5/2 plus f of 7/2. That's just converting it into a fraction to make this easier to calculate. If I plug 1/2 into the original, which was x cubed, this is the graph of x cubed, I would get 1/8. This one would be 27/8. This one would be 125/8. And this last one would be 343/8 if you cubed all of those. And I did this ahead of time as well. This ends up being 496/8, which is the same thing as 62 units squared. OK, so those are the 3 different types that I'd like you to know. So left, right, and midpoint. And notice how in each one I drew a picture of like the interval, and I looked ahead to see which numbers you're actually going to be using. So left used these, and then for this picture, the right ones were these, and the midpoint, you just grab the number in the middle for all of them. All right, we're going to continue on with some more examples, and I'm going to eventually show you how to take the number of rectangles to infinity so we can get the exact area. So I'll see you soon. So now I'm going to begin by giving you more notation and relevant formulas that you're going to need for this lesson. So let's begin that section. So we define L of n to be the summation from I equals 0 to n minus 1 of f of xi delta x. And R of n is equal to the summation from I equals 1 to n of f of xi delta x. So these are going to be the left and right Riemann sums, respectively, over some interval a to b. So let's talk about some of the notation here in case it's unfamiliar. Some of these pieces we've went over already. So remember, n is the number of subintervals. So in our previous examples, n was 3 and n was 4, but n could be any number. So n is just going to represent the number of subintervals, and that comes into play into these formulas. And then we also have xi. This is going to be your representative x value for each rectangle you're choosing. So the formula for that, for this, is going to be x of I is a plus I delta x. So this is how I was drawing that. I was drawing that picture before, and I was choosing the correct x values. So this formula tells you each x value to pick from your picture. And also, in addition, because I've talked about the left and the right approximation, I'm going to talk about the midpoint one as well. So in addition, we're going to define m of n to be the midpoint. So our midpoint Riemann sum. And that's going to have the formula m of n is the summation from I equals 1 to n, f of xi times delta x. And delta x and n are unchanged from what they were just above. However, x of I, the x of I representatives you pick, the formula for that works like this. It's a plus delta x I minus 1/2. So this will help you select which x's you choose if you're using the midpoint approximation. So this formula only pertains to m of n, whereas this formula pertains to both of the left and the right Riemann sum. Okay, and then this symbol right here, this symbol sigma, just means that we're going to add up all the pieces together. And you saw that we were doing that in the previous examples. You take all 3 rectangle areas and add them up, or all 4. This is just shorthand. to explain that you add up all the pieces when you're done. Okay, and there's a theorem here, so this is going to be theorem. So let A be the area, so the area under the curve f of x from A to B, where we specify that f of x shouldn't be negative for all x in the interval A to B. Then we have that the limit as n goes to infinity of the right Riemann sum equals the limit as n goes to infinity of the left Riemann sum equals the limit as n goes to infinity of the midpoint Riemann sum equals A. So all I'm saying is if you take any of these estimates that we've talked about so far, you make the number of rectangles infinite, like as many rectangles as you can make, then all of these Riemann sums approach the true area. So all of them converge eventually to the actual area under the curve. So I'm just saying they're all equally good in that regard. All right, let's take a look at this example. So in this example, we're going to express the area under the curve, 3x minus 2, from 1 to 3, using n subintervals. So this time, I'm not given a number of intervals, OK? So we're going to have n subintervals. Then we're going to use it to calculate the actual area under the curve. So we're going to take the number of subintervals, and we're going to take it to infinity and get the true area. All right, so let's draw a picture of what's going on here. So I want to draw a picture of the graph. So I'm going to start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I need any more, I'll draw more later. And I need to go 1, 2, 3, because my interval goes from 1 to 3. If you plug in 1, you get the value 1. And I have to go by my slope of 3. So if I plug in 2, I get 4. So 2, 3, so I see 1, 2, 3, 4. And if I go 1, 2, 3 more up, it's like this. So this is a picture of the graph here from, I've got at least from 1 to 3 here, and I've got some more going in either direction. But we're interested in the area under the curve here. OK, so we're going to use just n subintervals this time, but I'm going to use the right Riemann sum. So the formula for that is the summation I equals 1 to n of f of xi delta x. So I'm going to use the right Riemann sum to express the area of under the curve of this equation. So my delta x, remember the formula for that is b minus a over n. b minus a is 2. And this time n is n, so I don't get to plug in n. I'm just going to leave it alone. And also, let's grab our second formula here. So to pick the correct representative xi's, I use this formula, which is going to be a. This time a is 1, right? I have 1 for a and 3 for b. I'm going to grab 1 plus I. This is just some index. This just tells you which subinterval you're on. So I times, and then delta x. Here I just calculated as 2 over n. OK, so continuing here, I get r of n equals summation I equals 1 to n. I'm going to plug in what x of I is here. So that's what I found right here. This is going to be 1 plus 2I over n times delta x, which I found that to be 2 over n. And I have room, so I'll do one more step here. So this is I equals 1 to n. I need to plug 1 plus 2I n over n into the original f of x function. That's f of this. So I'm going to get 3 times 1 plus 2I over n minus 2. So that's what happens when I plug this into the function. And that's going to get multiplied by 2 over n. I'm going to go up here because I'm running out of room. So this is going to be r of n. I don't want to go too high so you can't see it. Here we go. This is going to be the summation I equals 1 to n. Here I have, if I distribute this, I have 3, and I have a minus 2. So I'm going to get 1. And then I do 3 times, I'm distributing here, 3 times 2i over n, which is plus 6i over n. And this is still all multiplied by 2 over n. So now I can take this 2 over n, distribute it in like this, and I'm going to get the summation I equals 1 to n. 1 times anything is itself, so 2 over n. And then I'm going to get plus 12i over n squared. OK, so from here, what I'm going to do is I'm going to use a property of the sum, where you can split the sum up over 2 things being added together. So I'm going to split this sum up, and it's going to be I equals 1 to n of the first term, so 2 over n, plus that same sum, I equals 1 to n, and it's going to be 12i over n squared. OK? So that's one property of the sum that you can split it up like this. Another property I'm about to use is that you can factor out constants. As long as the actual term in here doesn't depend on I, you can bring that up front. So for this first one, I would get 2 over n, summation, I equals 1 to n of 1. That's because I've factored out the entire 2 over n. And this would be plus the summation I equals 1 to n of I, and then 12 over n squared. That doesn't depend on I, so that can be brought in front. So I have this. And now to calculate this, I'm going to look at each piece separately. This right here is, I'll write it down here. So the summation I equals 1 to n of 1. The other one I have is this one, which is the summation I equals 1 to n of I. So we need to calculate what these are. For this first one, it's like you take the number 1 and you add it to itself a total of n times. So n is how many times you're going to have 1. So if I have 1 and I'm adding it n times, this piece is just going to become n. So I'm going to get 2 over n times n. So this became n. Then I have plus 12 over n squared. What is this piece going to become? Well, this, I plug in 1 for I get 1. Then I would move up to the next one, and I'd get 2. And you'd keep doing this until eventually you got to the last number here, which is n. Remember, this is just a condensed form of writing a bunch of numbers added together. That's all this is. It turns out that this is actually equal to n times n plus 1 over 2. So you can check that for small n if you want. But that's what this is equal to. So this gets plugged in here. OK, and then we continue from here. So I'm going to simplify as much as I can. The n's cancel, and I get 2. Here I get 2 cancels from the top and the bottom, and I get 6n squared plus 6n over n squared. That's what that second term becomes. Now remember, the area, the true area based on this theorem over here, is what happens when you take one of these Riemann sums. This time I'm using the right one, but it doesn't matter which one. You take one of these sums and you take n to infinity. You take the number of rectangles or subintervals to infinity. So my area is equal to the limit as n goes to infinity of r of n, which is the limit as n goes to infinity of this expression that I've made. So this is 2 plus 6n squared plus 6n over n squared. What is that limit equal to? Well, 2 is unaffected by this n going to infinity. So I get 2. And then we need our horizontal asymptote rules, right? As n goes to infinity, the powers match. So what does this limit go to? It goes to 6, which is 8. So the actual area, the true area, if you had infinitely many rectangles, it would actually be 8 under the curve. Now, that's great. We actually could have figured that out ourselves, though. If you look over here, I chose an example just so we could verify our answer. So I'm going to creep down here. Notice we have 2 shapes here from 1 to 3 of this curve. You have this triangle. The height of the triangle is 1, 2, 3, 4, 5, 6. And the base from 1 to 3, it's 2. So the area of the triangle is 1/2 base times height, which is 6. And then down here, we have this little rectangle that is the other part of the area. So rectangle, base is 2, height is 1. So So base times height is 2. So together, the total area is indeed 8. Now, you might be mad because I did all that calculation and got 8 as well. But in general, your curves are not going to look like this. Like, you're not going to have this thing that breaks up into perfect, perfect shapes like this. So you're going to have a curve in general. And you're going to want to be able to do that because we might not be able to use geometry like I did just here. OK, but it's good to know that we got the same answer that we're supposed to get. My last example is just an application. So suppose you want to estimate the distance traveled. Then what I want you to know is that the area under the curve for velocity, or under the velocity curve, I don't know why I phrased it like that, on the curve velocity, it gives you the total distance traveled. So I want you to know that the area under the velocity curve is the total position traveled, or the total distance traveled. We always go back to position when we talk about velocity, but I want you to know this. So suppose you have this example. The odometer in our car is broken. However, you want to still estimate the distance you travel over 30 seconds. Luckily, your speedometer still works. You know how fast you're going at certain times. So you record the times. So this is how fast you're going in feet per second. So 25, 31, 35. These are different speeds at specific time intervals. And we've marked down what's happening every 5 seconds. So you can approximate the total distance you travel by using a Riemann sum. And we could use either a left or a right Riemann sum. This time, our delta x, I guess I'll call it delta t this time, because time is the variable. It's 5, because with each of these spacings, I've had 5 seconds between each time I've recorded the speed. So it just depends which Riemann sum you want to use. You could use left or right. So if you use the left one, this is our left approximation. The way you approximate the distance is you would assume, OK, we're about at a constant speed from 0 to 5. We'll just assume that. So then I take the width of my rectangle, which is going to be 5, and I multiply it by how fast I was assuming to go for that whole interval. So the first speed is 25, ... and then you'd go all the way to the final left endpoint. So here's my final interval. The one on the left here is 25. So you do 5 times, oh, sorry, the one on the left here is this 46. That's the value, so 46. So the approximate time traveled would be 5 times, they all have this 5 in common. It'd be 25 plus 31, and I'm just reading across the entire chart, 35, all the way up to 46, which is my final left one. And I calculated that ahead of time. That's 1,135 feet. The other approximation we learned is the right-hand one. So if you wanted to do the other approximation, that's perfectly fine. So for our right approximation, you still have the width of 5. But this time, all you're going to do is you're going to look at each separate interval. So say the first one. And you look at what's happening on the right. So it's 31 and then 35. So in this case, for the right ones, the 25 is the one that gets excluded. But you include the 41, because on my final interval, 41 is on the right. So the difference is the left one doesn't include 41 on the right here in the calculation, and the right one doesn't include the very left one. So this one gives you that for the total distance. And one would assume that the actual total distance is maybe somewhere in between those two. OK, thank you for sticking with me with Riemann sums. I hope this was very helpful in constructing the different Riemann sums and using these formulas. There's quite a lot, but we'll practice more in class, so don't worry. Please try your lecture quiz, and I will see you next time. Bye.